on paper, just learn it how to read the paper that I'm teaching you. So just one like glucose oxidase based immunosensor. So okay, I can download this. So you can access the papers, right, that I uploaded already.
Yes, sir. 5 papers are there. Yeah.
Okay, very good. So just see my screen. I just open it here. Is it visible? Can I see my screen?
Yes, sir.
Yes.
Yes, sir.
Okay. It is better. Just okay, I think it is fine. See. So if you open one paper, so how you will start reading? First see. So just when you download the papers, so you should have interest on this topic first, right? Like here you can see the topic is the glucose oxidase level based redox cycling for an incubation period free electrochemical immunosensor. So as you know, this title is very much related to with our uh, teaching topic, right? So it is kind of like you see the these things like glucose oxidase level based this one. Basically the glucose oxidase level, something I already taught you, right? Redox cycling I already taught you many things, and electrochemical sensor that I am teaching you in this course. So this topic is very much related to your, I mean, if you are expert, when you become the expert, or when you are looking for some new research area, so you have to think about which area you are interested. So as you see this one, so you can download this paper, right? First, then what you will do, first read the abstract of the paper. Because abstract means it is the summary of the whole work, right? Just few sentences, maybe 15 to 20 sentences, I mean, just the summary. So see that here, like here they mention that catalytic reaction of enzymes levels in enzyme linked immunoglobulin assay require a long incubation period. So generally for the catalytic reaction, for the reaction enzymatic reaction, you need the incubation. Incubation means you have to we will drop the mixture of the solution on the surface and you have to wait for some time. Incubation means you have to wait for some time, like 10 minutes, 15 minutes, or sometime maybe half an hour, 1 hour, or 2 hours. So this is called incubation. So why we need incubation? Because of some reaction time. Because there's so many chemicals involved, right, in these reactions. So maybe for getting the full reaction, we have to wait for some time. But in this biosensor, they developed something that is incubation period free. It means we don't want any kind of incubation, just drop the sample and immediately we can measure. So here we can measure immediately. That's why it is called incubation free. So it is already described here in the abstract. So this, all the sentences, all the reagent, these things they mention here. So I think you can easily understand the abstract parts. That's why they mention everything, that they use this chemical. It does not require any kind of incubation. So they checked actually 0 minute, 5 minute, and 10 minute, different time interval, and they compared the data and they found that the 0 minute incubation is fine for the detection, right? So whole summary of their work is mentioned here. So if it is clear to you, then what you will do, you can check first their schematic diagram. No need to read the whole paper at the first time. Otherwise, sometime maybe, suppose you are not getting some idea from the abstract. Suppose you read everything, but you didn't get much idea. Then what you'll do, go to their schematic. diagram of their work. The first schematic you can see here. So they use some I2A electrode. They immobilize some avidin and they use antibody for immobilization. And they detected CA125 and they use secondary antibody that conjugated the glucose oxidase. Which without reading you can understand, right, guys? Right?
Yes, sir.
Yes, sir.
Yeah, this kind of thing. Without reading, you can understand something. Means like this way, you will be motivated. Let's read the paper. Sometime, so if you understand this picture, now if you go back reading their scheme and their writing, the history, everything, then in your mind it will be reflected the image. Oh, they did like this way. Then you can understand easily all the sentences. So don't go fast the sentences. So please check first the schematic. So how they did? No, they use this kind of thing. They use some ruthenium hexane mediator, and they use glucose some substrate, and this glucose reacted with the glucose oxidase. And in the part B, they mentioned that oxygen also can react with glucose oxidase. So something like this, right? So some idea you will get. Okay, then see some any other figures. So you can see some other figures also, you can check. So they measure charge versus time in chronocoulometry, the method they use. Then after that, maybe maybe it is not clear to you, then leave it. So they use chronocoulometry, that you can understand. Then go back, then go and check their image. Oh, they actually they optimize the pH, they optimize the glucose concentration, they optimize ruthenium concentration. So something like this, right? Okay, then check. So they use the chronokilogram. Okay, fine. Okay, so this is the full summary you can see at a glance, right? Okay, done. Then okay, so you read the abstract and you check their schematic diagram and the images. Now go back. Now let's go the conclusion. Conclusion. Why I'm saying conclusion? Because it is again the summary of the full result of the papers, right? So let's read the conclusion. So what they say? This study demonstrated the incubation period of the catalytic reactions levels can effectively minimize. So this blah blah these things they mention, and they mention that 0 minute is 0 minute case detection limit. What will be the detection limit? So everything they mention. So then the whole summary, it will be visible in front of you that what actually they did. Presented this paper, why they work on this topic, right? So as you are motivated now, okay, so these things, it is in the whole paper, this kind of point you will get. Okay, now go back the introduction part. So basically introductions of the papers means it is kind of sometime they actually summarize many other previous work. When some people did some work maybe in the similar topic, but they have some drawback. But what is the novelty of this work? Something like this they will mention in this part, in the introduction part. So in the introduction, so basically they will mention first some reported work. So some, you can see some reported, they will cite all the reported work. You can see there is so many citation, 1 2 3 the 6 8 4 8. You can see there is so many other journal they cited because they did some similar work, but they have some other drawback, or they face some challenges they already may overcome, but you wanted to do some different way. So this kind of points you will get from the introduction part. Yeah, so one paper, it is not like this that you will get only one idea. It is kind of they gather so many other problems, other ideas, and other challenges. So other people, what they are doing in this area, everything they will gather, all the information. That's why basically when you read one paper, you can read almost 20 or 30 more papers. So if you sometimes maybe you can see the first sentence. Catalytic reactions of enzyme labels are used to enzyme link immunosorbent assay, that is called ELISA, to generate a large number of signaling species per target. So they mention this sentence. So what's the meaning of this? Maybe it is not clear to you, but they cited 1, 2, 3. So then you can go back the references. These 1, 2, 3, if you check these 3 papers, then you will get more idea basically on the ELISA method, because this first sentence they mainly specified what is the ELISA. Okay, so you can read this paper if you are interested. If you think, okay, I don't want ELISA too much, it is fine for me, then leave it. Then you can read the other sentences. So see the another one. Horse radish peroxidase HRP, that is one enzyme, is commonly used as an enzyme label for this purpose. Generally for the maybe enzymatic reaction or redox cycling enzymatic reactions, horse radish peroxidase is commonly used. But how you will prove? You should have some reference, right? So if you check 6 to 8 these all the references, then you will get that people actually use this enzyme for the biosensor development. So then you will, so from the one paper, that's why you will get many other paper. So you can read, or if you are not interested, you just read these sentences. So like this, you will get the idea from the reference introduction part. And experimental section. If you go here, so they use mainly the chemical solution. So if at the beginning, as a beginner, maybe you are not really much interested on the chemicals or their compositions. So maybe in that case, maybe you can leave this part. But when you will be a researcher, but when you are wanted to develop by yourself any kind of biosensor, that time you should know this kind of chemical structure, what the percentage they use, these things, what the pH of the solution, you should know. That time you should read the chemical and solution. But as a beginner, you can leave this part. Okay. So after introduction, then you can go basically. So here the preparation of the immunosensor. So you can come to here also. So how they prepare the sensor one by one. This is basically the experimental procedure. Then you can come the resultant discussion. Because you already learned that what is the main topic they discuss in this paper, how they developed everything. And now if you come the resultant discussion, they will explain why they are getting this kind of result. Basically the explanation part here. Sometimes maybe explanation part is not too much clear to you as a beginner. So don't worry, you can go to the next part. But right now I am here. If you don't understand any paper, so you can ask me that this explanation is not clear to me, so I can explain you. But if you want to read some papers, I think this is the main technique. So first, choose the title. If you are interested in this topic, then go to abstract first. Then go to the schematic diagram. Then come to the conclusion first. Then after that, after the conclusion, then come back to the introduction part. Then come slowly one by one, like fabrication, result discussion, like this. Clear, guys?
Yes.
Okay. So do you have any questions now? How we can read the papers? I already uploaded few papers, so please read them. Also, please download some papers. Now I will show you how effectively you can download some papers. Okay. So just go Google. So some very good biosensors, like I can show you, like biosensors and bioelectronics. Okay. So biosensor bioelectronics is a very good journal in the sensors. So you can click here. So you can write down this paper's name, biosensor bioelectronics. Then you can go the view articles here. So here maximum all the kinds of the sensor papers are here. And different kind of devices they explain. Go to view articles. So here you will find all the articles they actually published. So here you will see like article in press. Article in press means that just the authors they submitted and accepted, just accepted. So this is very new papers, and latest that already published papers are here. You will get some most downloaded, most favorite journal, most favorite paper in this journal, top cited journal papers you will get. Also, you can search in your own topic here in the search column. So here you can search like electrochemical biosensor. Okay, you can search here. Guys, is it fine? Everything clear to you? If you're not clear, you can ask me the
Yes.
question immediately. Okay. So electrochemical biosensor, you can type and enter. See, now you can see here so many papers they actually you can find. So you can choose one. If you are, means you can choose one that is you are interested. So like this, so you can choose one paper you can read and you can present. One day I will give you one date, and that day you have to present one paper. So like this, so you can choose one paper and you can read. So this is one journal, that is Biosensor Bioelectronics. Another journal I will mention here, like Analytical Chemistry. This is very good. This is one very good journal in the biosensor. So please try to or you can note down this paper name. So this is the American Chemical Society ACS papers. This is ACS publications. Here also you will get all the kind of as soon as possible that latest publication, current published papers, most cited papers, and all kinds of paper you will find out here. But if you want some specific paper name, you can mention here. Like you can search here like same way like electrochemical biosensor, like this way. So you can search, and so here if you search you will get see electrochemical biosensor, many journals are here, so you can read basically different technique available. Okay, so this is one very good journal. Also in the AC you'll find so many other journals in the ACS publication. Just click in the ACS publications, just click. Okay, so in the ACS publication there is other journals also that they where you can find out they're publishing actually many biosensor papers, electrochemical biosensor papers. So you can find out so many other journals available. Uh, another very good publication share available, that is I can say the RSC publications. RSC publications, and that is called Royal Society of Chemistry. RSC publication journals. So here the same way there's so many journals are available. So same way you can search here in the search column electrochemical biosensors. So if you search, so you will get different kind of the paper name: flexible electrochemical biosensors, carbon nanometer based biosensors. See, okay, it's very simple, right, guys? Is it fine?
Yes, sir.
Yes, sir.
So like this way. So you just note down. So RSC publication, so on. So in the RSC there is so many other journals available. So you can. So if you click here in the publishing, so you will get so many other journals name. So like this way. Or very simply, if you do, sometimes maybe you cannot remember the journal name, just Google. In the Google, you can search some electrochemical biosensor, by electrochemical biosensor for cancer detection, redox cycling based biosensor for disease diagnosis, or some electrochemical biosensor for device development. So this kind of keywords, you can use for your searching. Guys, any questions?
No, sir. Understand.
Okay. Okay, good. Then let's start some new topic today. Okay, I think someone you asked me the multiplex sensor, right?
Yes, yes, sir.
Okay, so I think I will describe you. So what is the multiplex sensor, right? So when you are going to detect more than one analyte, there is multiple analyte, right? That is called multiplex sensor. So how you can design the multiplex sensor? So first come to the design. Okay, suppose it is a, you can choose any kind of substrate, maybe any plastic substrate, any glass substrate. Suppose it is ITO, indium tin oxide, right? Indium tin oxide means it is the glass. On the glass, it is indium tin oxide nanoparticle coated, right? Now we can pattern, pattern, patterning. You know, the pattern means some design, right? You can do. So the whole surface is the nanoparticle coated. But if you pattern means, so maybe like this, like this, like this, like this. Yeah. Maybe like this way. So pattern means a whole surface, but you can use some technique that is called some lithography technique. So you can use some mask. Then you can actually scratch that. No, that is not scratch. You can just remove the nanoparticle from this side. Huh? So from this position, you are actually removing all the nanoparticles. So it becomes the non-conductive, right? So this position become the non-conductive. This position. So only ITO will be there, only this position. So ITO will be there, I mean nanoparticle will be there, only this position. This is called the pattern method, right? There is so many patterning method like lithography technique, the chemical vapor deposition technique available. So only your nanoparticle will be here, 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 and they will be connected like this way. They'll be connected, right? So what you can do, one pattern, this one, you can use as a working one, and this one you can use as a working two. So in the working one, so you can immobilize one antibody, antibody one, and working two, you can use another antibody, antibody two. So this antibody, suppose it can detect like malaria, malaria. And this antibody, suppose it can detect dengue. Huh. So, so what you will do, you can draw, you can modify this surface with this malaria antibody and this surface with dengue antibody, right? Now, so this electrode it acts as a reference electrode. This electrode will act as a counter electrode. So they are common. These two electrodes are common for these two, working one and working two. So they, this is the, these two electrode, they can behave like one is the reference and the counter for both of the working electrode. But these two working electrode will the different one because they're coated with different antibody. Now you will drop the sample. Like you are dropping the blood sample. And you wanted to check at the same time the malaria and dengue concentration on your blood sample. Right. Now if you drop the blood and if it contain malaria, then it will bind here, but it will not bind in the working two because working one is specific for malaria. But if you have malaria and dengue both, then malaria will bind in the working one and dengue will bind in the working two. Dengue will not bind in the working one. Right. So when you connect this one with the potentiostat, that is the detector, then you will see basically two curve. Right. You will see basically two curve. Like one chrono, maybe chronoamperometry, here maybe you will see another chronoamperometry. So this is for malaria, working one, and dengue. This is for working two. So working electrode one and working electrode 2, right? So 2 chronoamperometric curve you will get for this multiplex biosensor. Now you will already have your calibration curve that like the single detection you did last time I taught, that you have to already, you should have this curve in your hand. Now from this data you can predict how much malaria and how much dengue present. Maybe in your blood sample you have malaria but you don't have the dengue, then in this case malaria case you will get the very high signal, but dengue case you will not get signal, very low, almost background, right? So like this way you can confirm that your sample contain both biomarker or no. Now you can increase the number of the working electrode. Maybe here another one, working 3, here working 4. So at the same time, malaria, dengue, then you can go for maybe any other maybe like viral detection. Right now it is very important. So you can maybe immobilize any COVID-19, that virus specific some antibody, right? And here maybe you can some influenza virus specific some antibody you can detect. You can immobilize on the working 4. So what will happen then? Then you will get the 4 curve. So working 1, working 2, working electrode 3, and working electrode 4. So here also you will get the chronoamperometry. So at the same time you will see 4 chronoamperogram. And you already have the calibration curve. So from that calibration curve, like 4 calibration curve, you can, you will have the software in the instrument that display. So they actually automatically, because of they automatically they will show you digital value, how much concentration in the working 1, how much in the working 2, how much in the working 3, how much in the working 4. So this is the utility of the multiplex sensor. No need to detect one by one. Means by one shot you can get the 4 concentrations of the 4 different biomarker. Clear, Suman?
Yes, sir.
Okay, very good. Any questions? Any other guys? Because Monday is your Monday, we'll have the exam. So if you have any question, you can ask me today. Because every Wednesday we'll discuss.
Sir, I had one question. I could not clearly follow the graph you showed in the lateral flow assay.
Okay. Which one? Lateral flow assay.
Yes, sir.
Which one?
Sir, lateral flow assay, you showed a graph where there were multiple peaks after this slide, I think. Yeah, 70.
Huh.
70.
Which graph is not clear?
This bottom graph.
Which one?
The bottom one, the third picture. Yes, sir, this one.
This one. Okay. Okay. I'll tell you this one. Yeah. So this one basically that is unwanted reaction that I already told you. So this signify this cross. See, I told you already when we developed some redox cycling based, in this case ECC biosensor. So our main goal, signal to background ratio should be very high. So for that, background should be low and signal should be high. So how we can get this one? So T shape. See, this is the this will be present in the background also, right? So T shape, ruthenium hexamine 3, it will present in the background. So basically they should not react to each other, right? And T shape itself, it should not react on the surface. That I mention here. So it is kind of the energy diagram I mentioned. Actually, that is T shape means it can oxidize in the lower potential. I mean negative. I mentioned already some potential window. So here is the positive potential window, is the negative potential, right? So negative, more negative means generally they can generate their current, or they can oxidize in the this region, negative region. If you go positive means they can oxidize here. So I mentioned ITO is the highly positive because they are almost very inert and they can oxidize at a very high potential. That's why I put the very high positive. Then ruthenium, then methane blue, then T7 will come. But that's why I put that which one will come first and which one come lower portion. So negative means they can oxidize easily in the negative side, and positive means you need a very high potential to oxidize them. So for this biosensor, T shape should not. So see, come to the picture 1, picture 2, and picture 3. Come to the picture 1. So as I mentioned, to generate the lower background, T shape should not react on the surface, ITO surface. So that's why I mentioned, let's drop it, T shape to ITO. This one cross. It means this energy diagram implying that T shape should not react with the ITO. Now, another one. T shape should not react with ruthenium hexamine, right? That I mentioned here, as I told. Because T shape and ruthenium hexamine 3, they will be our starting material. They should not react to each other. Right, Somo, can you remember?
Yes, sir. Yes, sir.
That I mentioned here cross. It means T shape when you go to the ruthenium hexamine, it should not react. Okay. But I mentioned it is very like this arrow, if you see, they are going smoothly. They're going smoothly, no cross here. Why? So T shape will react methane blue will react the ruthenium hexamine then will react the ITO. So this reaction should go smoothly. I mean, the whole redoxide reaction should go smoothly for generating high signal to background ratio. It is implying this one. So this reaction should go smoothly, but this reaction no, this reaction no. Okay, so from this figure you can understand which reaction is the unwanted reaction and which one is the wanted reaction. Clear?
Okay, so from this diagram, once we have this diagram, we can also optimize on our potential. So we can optimize on the potential that we have to work with in order to avoid these interfering interactions, right?
Yes. That potential nature also you will understand from this diagram. Where they are actually oxidizing. From this you can understand the methane blue oxidize first, then ruthenium hexamine, then ITO. So some sequence actually you will get some idea, rough idea you will get. So it is some kind of informative energy diagram. Clear now?
So this is the more the difference in potential, the less favorable the chemical reaction is. So from that way,
Yeah.
we can.
So if you say maybe lower potential means it can be easily reduced. They can easily oxidize basically. So if some potential like methane blue here, right? So if you maybe they can easily oxidize when you apply this potential. But ITO potential is here, right? So you need high potential to oxidize them. So it is so this kind of position you can understand where is their actual position in the potential window.
Yes, sir. So from this time also because of the fact that ESEP and ITO has a more higher potential barrier, so to say. So then chemical reaction is not favorable. So these things also we can understand. Right?
Yeah. That's also good, right? Very good, Somo. It is very good information. Like this way, you can predict something because they are a very high difference. They cannot react to each other.
Okay,
Very
sir.
good. Very good. Yeah. Okay. Clear now. Let's go. The new topic then. Today's topic. Anything need to clarify or anything I can explain again? No. No. Right. Okay. So today's new topic is a strategy for the electrochemical detection. See, just now I am telling you the potential window. So what is this window means? The range you are using for your experiment, right? Suppose here is the 0. So in this area negative, in this area positive. See here, if your cyclic voltammogram, so this is the cyclic voltammogram, right? CV. So here you can see very high oxidation, but there is no reduction almost. But that's fine because some compound can show very good oxidation, but no reduction, like the glucose I mentioned, right? Because they are the irreversible. Because they are irreversible, right? Can you remember? So if it is reversible reaction, if it is reversible reaction, then you will get very good oxidation and reduction because they can reverse oxidation reduction. But if the reaction is irreversible, then you will get a oxidation very good curve, but there is no reduction curve. Right? Can you remember? I taught you, right? This one?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah. So in the exam, I will ask like this. So this, from this cyclic voltammogram, you can easily understand the substrate behaves like kind of irreversible reaction because there is no reduction curve. Now, the position of their peak. You can see the peak of their position in the very lower potential, right? Almost negative potential or very close to 0. But if somehow the same thing, I mean the same electrode, same substrate, but maybe there is some change happen on your substrate surface, electrode surface, so you are getting this kind of cyclic voltammetry. So what's the change? Cyclic voltammetry 1 and cyclic voltammetry 2. What's the change? Their position, right? Guys, their position, right?
As a peak current also.
Good. Their peak current. So one is the position, another is their peak current. Basically, see, biosensor in this case, it's fully depend on your observation. And accordingly, you can explain the behavior that we are doing in the lab. Means we are checking the cyclic voltammogram of a compound on a substrate. Then from the behavior of their cyclic voltammogram, you have to explain why you are getting. That I'm guiding you today. How we can explain this? See, first of all, number 1 and number 2, these two cyclic voltammogram, as I mentioned, their surface same, compound, the substrate same, but something happened on the surface you don't know. Maybe today, maybe you made one sensor surface and you kept it overnight. And then morning you came to the lab and you checked the cyclic voltammogram, right? You found number 1 is the yesterday and today is this one. Then you are confused. Why you are getting like this? Then one thing you can explain, this is happening because of slow electron transfer or tunneling. Why you are saying tunneling? Because electron tunneling, right, from solution to the surface. Anyway, this is the slow electron transfer. So because of slow electron transfer, they can move towards the positive side. But if it is the fast electron transfer, then you can go back again to the left side, negative side. Negative side means you can easily you can oxidize. Positive side means more and more positive means you have to apply more and more potential. More positive potential you have to apply. You need more energy. Means their activity very low. So low catalytically active. So the number 2 is the low catalytically active. Number 1 is the less catalytically active. Then you have to investigate what happened on your surface. So how you can investigate? Maybe you have to characterize the surface. Maybe you have to check some maybe some surface phenomena you can check. Surface phenomena you can check like some ACM image. I think you know. ACM in scanning electron microscope or AFM, like atomic force microscope image, something you can get. If you get this kind of the image of your surface, you can see on your surface maybe whole night some dust, some contaminant, they deposit it on the surface. Or maybe some organ, maybe accidentally you touch the surface. Maybe you touch by your bare hand, your bare finger. Because of the finger, maybe some oily nature your finger. So they actually, you touch the surface and the by some dust. That's why their activity decreased. And you are getting this kind of cyclic voltammogram behavior. Clear, guys? Hello, students? Is it clear why you are getting this kind of things?
Yes, sir.
Sir, can you repeat it one?
I repeat. Okay, okay. Just let's repeat. Okay, let's discuss it. So I said that from the cyclic voltammogram we can understand the activity, right, of the surface. So you can do the same surface. I mean this surface you can keep the constant. You can keep the same substrate. I mean like the glucose you can oxidize on the surface. But maybe today you are getting like this, and tomorrow you can get like this. So, but if you get tomorrow like this, it means the surface actually deactivating. Their electron transfer is slow. Here the slow transfer. If you get the lower current and higher potential. But if you get in the lower potential and higher current, something like this, so it is called the high electron transfer and highly electrocatalytically active. Electrocatalytically active. These two phenomena we will get these two observe. I mean, we can observe these two phenomena. So if you think this is the zero, so if you go lower, so this is the highly active, higher transfer rate. Why this happened? This happened because of your surface can be deactivated by some other contaminant or by some any other way. Also, you can do by knowingly or unknowingly. See, unknowingly means maybe somehow you touch the surface, electrode surface by your bare hand, or some contaminant may come from the air, from the environment. So they can deposit on the surface, or they can deactivate the surface. That's why you are getting like this. Also, knowingly, also you can do like this. And sometimes maybe you don't need the highly active surface; you need the lower active surface. So in that case, you can treat the surface with some chemical. You can use some chemical. That kind of chemical can deactivate the surface nature. I mean, their catalytic activity nature will be deactivated. But how you can measure that your surface deactivated or not? That you can measure by the cyclic voltammogram. So if you get number one cyclic voltammogram, it means your surface is very highly active. And after the deactivation, if you get like this CV, it means your surface deactivated. Opposite way. Maybe at the beginning, you are getting this kind of cyclic voltammetry. But you want to activate your surface. So how you can activate your surface? You can chemically treat the surface. You can wash the surface with some chemical. I think I already taught you. We can clean the surface with some ammonium hydroxide plus hydrogen peroxide plus water mixture, right? So like this way, if you can treat the surface, they can remove all the contaminant from the surface. Then your cyclic voltammeter can go back here. I mean, here's at the beginning you are getting slow transfer, but after cleaning you will get the very high electron transfer rate because you are removing all the contaminant. Or maybe two things. Number one, number two. Maybe number one, I mean, if you consider this is the number one, maybe here some gold nanoparticle coated. That's why you are getting high transfer. But number two case, your surface is a bare, no gold nanoparticle. Then you will get number two kind of cyclic voltammetry. Clear now?
Yes, sir.
Yes.
Yeah. Okay, let's discuss this one. It is very good fundamental principle I am teaching you. So here actually I mentioned the bottom. This is the nanoparticle. Maybe it can be very close to the surface. That's why you are. I mean, there is so many. I mean, different way you can design your surface. Or while you are
Sir,
designing your
hello?
biosensor, yes.
Sir, I have small doubt.
Hmm.
Sir, while discussing impedance spectroscopy, we said the RCT value will be increased because of the potential as the reaction continues. How is it different, sir, compared to this one?
See the impedance case. See impedance case, as I mentioned that. Okay, let's explain it. Very good question. See, like impedance case here, your antibody, right? Then you immobilize the antigen. So what will happen? Okay, let's remove the antigen, right? So here antibody. Now, very good question, very good. So now here antigen, right? So this is the number one and this is the number two. So so tell me, so here RCT, which one RCT1 and RCT2, which one highest and which one lowest?
One will be the highest, sir. Sorry, second will be highest. First will be lowest.
So second, first. So this is the second, this is the first, right? So it is, you will get this kind of behavior from impedance. Now, if you measure the cyclic voltammogram, so if you measure cyclic voltammogram, so you will get similar like this. So like glucose, right? So from the number one, you will get like this, and from the number two, you will get like this. So this is the number one, the number two. So you will get like this. So from the CV, you will get difference like this, and from the EIS, you will get like this. So that's why if you read some papers, people are showing the both result, impedance result and cyclic voltammogram result, both they are showing. But sometime very minor change, cyclic voltammogram is not, you cannot differentiate. Maybe if you change the concentration of some target concentration, maybe number three, so maybe number two, number three, they can be coincide. But in the EIS case, you can differentiate them. That's why people are using EIS, because it is very sensitive than cyclic voltammetry. Clear now?
Sir, how we will differentiate, sir? This potential change is happening because of the antibody or the dust, or we as we discussed.
Oh, no,
How
no,
will
no.
how
No. So that's why I'm saying when we are developing the biosensor, we have to be very careful. That's that's why some contaminant, some dust, or some other outside problem can affect your sensor efficiency. That can mislead you. So you have to be very much careful. You have to store your. That's why packaging of the sensor material is very important. When you're commercializing any sensor, your packaging system should be very unique and very carefully done. Otherwise, the contaminant, outside problem, they can affect your sensor efficacy. So you have to be very careful. That's why packaging is very important when you are going to commercialize your sensor. So yeah, you are right. Sometimes maybe outside material they can decrease the, I mean this I mean their efficiency. That's why maybe your uh, impedance can be increased. But you are thinking that concentration of target may be increasing, but it's not, because of the outside contaminant increasing the EIS. That's why your this cleanliness, your storing technique, packaging, this should be very carefully done. Clear?
yes, sir?
This is very important. Very good question. What is your name? I cannot see
Dushyant,
you.
sir.
This one.
Dushyant,
Good.
sir.
Yeah, because I'm teaching in the slides. When I'm teaching slide, I cannot see your face on my screen. Okay, very good. Very good question. Now let's go. Next one. See here, I'm showing that this is corresponds to this nanoparticles that is very close to the surface. And number two means nanoparticle can go to the far from the surface. And we can go back. I mean, we can enhance This is called the enhancement. I mean, it is not like this means your catalytic activity decreased. It is, but there is a way you can improve the activity. Maybe some chemical treatment, something else is there. I will teach you today how you can enhance the activity. Maybe somehow unknowingly or any accidentally your activity decrease. But you can go back. You can enhance the catalytic activity by treating the surface with some chemical or by some other method that I will teach you. So we can again transfer the electrons. Maybe you can go in between. So you can use some moderate chemical, or you can go back to the initial stage. Maybe we can use some very highly active chemical we can use. That thing I will teach you now. So this implies, yeah, maybe you generate some sensor that nanoparticle is very close to the surface, and some nanoparticle is very far from the surface, and some nanoparticle may be coated with some other material. That thing you can explain by measuring their cyclic voltammetry and their peak position. Okay. Clear, right? Any questions?
Yes, sir.
Good. Very good. Okay. Now enhancement. That just I told you that sometime we need enhancement, right? So we have to go back to our active position. So how we can enhance the activity? There is some way. So one method, some thermal treatment, some chemical treatment, some electrochemical treatment, and chemical treatment. So this kind of method we can use. So thermal means you know already that some heat treatment. So you can, you can heat the electrode surface at a different range, like 60 degrees, 70 degree, 100 degree. You have to optimize. It's depend on your electrode material. It's depend on your nature of the that's you have to do in your lab, and that is fully experimental. So you can design some experiment, and you can investigate their which temperature is the best for getting the high activity, right? So that you have to do. Electrochemical. Electrochemical means, so you can like say here like minus 0.3 volt to like say here like 0.9 volt. So you can scan the electrode surface within this volt, this potential range, maybe 20 to 50 scan. 20 to 50 scan means 1 scan, 2 scan, 3 scan, like this way. Maybe in the like 0.5 molar in sulfuric acid solution, any acidic solution, or in maybe potassium chloride, any in a electrolyte solution, or generally people prefer in the acidic solution, so that easily you can oxidize the surface, you can easily reduce the surface. So like this way, this is called electrochemical cleaning. Electrochemical cleaning. So electrochemical cleaning means just within few potential window, you have to scan 20 times, 50 times, like this. That you can optimize also, means how many scan is better for the cleaning. That depend on the material. So this is called electrochemical. So like this way you can activate your surface. Chemical. Here you can use some other material like as I mentioned here, sodium borohydride. So sodium borohydride, one reducing agent I taught you. At the same time, sodium borohydride can help you your surface. They can help you enhance the activity also. So that also one factor. So how, that I will teach you. That what's the mechanism of the sodium borohydride that can help to activate the surface. So that's what people are doing. Before using the sodium borohydride, they can dip the surface in the sodium borohydride solution. they can dip the surface maybe in a solution of sodium borohydride, and they can dip in the solution. Then you will get the highest activity of your surface. But another thing, not all the material can be activated by sodium borohydride. It is investigated already that sodium, that gold, platinum, this kind of metal electrode, they can be easily activated by sodium borohydride. But other other like carbon based or indium tin oxide, they are not that much activated by the sodium borohydride. So it's depend which chemical you wanted to use for activation. That depends on the material of your electrode. Clear, guys? Up to here, is it clear?
So the electrochemical once more, can you please do?
Sorry.
Electrochemical once more, please.
Oh, electrochemical thing. See, electrochemical means just you have to clean the surface in a, like as I said, like 0.5 molar sulfuric acid solution. You have to repeatedly you have to scan like 20 to 50 times within a potential window. Potential window means like minus 0.3 volt to around like 0.8 or 0.9. You can choose some potential. Then within this potential window, you just scan it. Like 1, 2, 3, 4, like this. So you just scan it. So after 20 scan or 50 scan, you can clean the surface with the DI water, and you can check the cyclic voltammogram. So before the electrochemical cleaning, maybe your CV will show here, but after cleaning, your CV will show here. It is like this. So this is kind of the cleaning method that can activate your surface.
Okay, so the electro part do not add a role in the cleaning or enhancement. It is for the measurement purpose, right?
Yeah, this is for the measurement.
Means it does not augment any extra cleaning or enhancement of the surface.
So generally, that's why for the development of the biosensor, you should follow any of the cleaning, any thermal cleaning, any electrochemical cleaning, or any chemical cleaning. You should follow any of it, because uh, when you're receiving the electrode from any industry or any other company, they are just sending the material to you, and sometimes they're very much casual for the shipment process, right? They are sending your electrode material. Maybe someone, they can touch the surface, but their packaging is not that much good. So after receiving the electrode material from any company or any industry, you should follow any one process to clean the surface. So the major threat is the contamination. Contamination is a big problem. So you have to remove this all the contaminant by using any of method. Okay. Clear?
Yes, sir.
Okay. Now let's remove everything. Okay. See here. So as I mentioned, that sodium borohydride actually can activate the surface, activate the electrocatalytic activity. You see here actually one sensor where we use the gold nanoparticle that conjugated with the DNA. Anyway, so if we see, if we dip for 15 minutes in 10 millimolar sodium borohydride in a carbonate buffer. Carbonate buffer means we need one buffer solution to dip in the this nanoparticle. We can dip in a buffer solution, and that may contain a 10 millimolar sodium borohydride. So this 10 millimolar sodium borohydride within 15 minutes, how much it can activate, you can see in the picture. So in the bottom one, this one, you can see that before. In the upper one, you can see this is the after. You can see their oxidation potential change and their current change lots, quite lot. See, too much change. This can be done within 15 minutes when you dip inside a sodium borohydride solution. And this is for gold nanoparticle. So why I mentioned gold nanoparticle? Because just I mentioned it's depend on the nature of your material. Now if you change the material, maybe their activation can be changed. So for the gold case, it can be changed like this. But if you change to the palladium, like gold to palladium, maybe activation time can be changed, their peak position can be changed. So it's depend on the material. So first focus on the gold. So gold case, it is very clearly visible that before activation, after activation, how, I mean, from the cyclic voltammetry, as it is shifted to left hand side, it means this is the highly active one. And the lower current and higher potential peak, it means is the very, very low electron transfer. And in the blue case, it is the highly electron transfer rate is very high, catalytic activity is the very, very high. So very high electron transfer and catalytic activity also very high. These two things. Clear? Clear, students?
Yes, sir.
Now see the mechanism. The schematic, how it enhances the activity. Actually, when we add the sodium borohydride, see, here actually we are showing the NH2, see, NH2 means just one substrate. Substrate that is called hydrazine. So before sodium borohydride treatment, we checked hydrazine that it's very slow. But after sodium borohydride, what happened? Actually, in the sodium borohydride, you can see there is 4 hydrogen atom. That hydrogen atom, actually, they can decompose and they can adsorb on the surface. See, they can adsorb on the surface. Because of these hydrogen adsorptions, actually their activity changing. So in this case, sodium borohydride actually they are actually not cleaning the contaminant. They are actually activating some different way. So you can remove the contaminant by some other cleaning method, like electrochemical cleaning or some mechanical cleaning. But here they are activating surface in a different way. Why the surface activity increasing? Because hydrogen atom actually they adsorb on the surface. And because of these adsorptions, this electron transfer rate become very, very fast. And this activation also can be deactivated. It is not like this, it will be like this. As I mentioned, means you can keep it a long time in the room temperature, but somehow some contamination can come. So it can be deactivated. It's possible. But you can activate them by sodium borohydride. Okay. So what's the mechanism? Sodium borohydride, actually they are hydrolyzing and they form the hydrogen atom. This atom can absorb on the surface, and because of that, thus there is one term I will say. This is called surface FSC, surface reconstitution. Surface reconstitution means when hydrogen adsorb on the surface or absorb on the surface, there is strain they can feel on the surface. Because of the strain, their activity actually increasing. So this phenomena is called surface reconstitution, and their catalytic activity actually increasing. Clear, guys? Hello, students. Is it clear?
Yes, sir.
Good. Akash, hello Akash Sharma. Hey Akash, are you there? No.
Hello, sir.
Hello.
Sir, I'm little bit confused about the syllabus. Sir.
Who is it? Vibhuti?
Yes, sir.
Tell me.
Can you tell me the syllabus of the test, sir, which will be going to conduct on Monday?
Monday means up to today. I mean, how much I am teaching you today
Yes,
from the
sir.
beginning. From the beginning.
Okay, sir. So it will be MCQ type test, sir.
Let's see. I'm planning this time. I will give you both some MCQ and some descriptive type.
Just same as the last test, sir. Like
Yeah, something like the last test. I mean, I will give you both tests because say in our course, uh, it is not like this only the MCQ. Maybe you have to draw something. You can design something right by yourself. So
yes,
that's
sir.
why I will give you some descriptive type questions also.
Yes, sir. And sir, the syllabus will be from the starting, sir, not like from the first test.
No, not for price. It will be but from the starting, I will give the some very few. But last few classes, you should focus more because I will give the more question from that part. Maybe last few after the test, I think I taught some signal amplification and up to today.
Yes, sir.
So from there, I will give you more descriptive type, maybe around 10 questions, 10 marks. And from the before the test, I will give you around 5 marks. Total 15 marks I will give you.
Okay, sir. Thank you, sir.
Mhm. Okay. But see, some of you the attendance. See, I think I should be careful. I should send the message to all of you because some of you are attendance is very low. Hmm. So I will sit one day. I will count how much your attendance because today only 34 students. So you have already one WhatsApp group, right? Right, Vibhuti, others?
No, sir.
Yes.
I
I
think no.
think no. I think you have, right?
Yes,
Elizabeth,
sir.
you have, right? So
Yes. Yes, sir.
please send the message that that I said. Otherwise, I have to be strict and send the message, and it can go to your faculty advisor up to you that. So in this case, maybe they will send the message to you that why your attendance is very low. Some of your attendance is quite low, and only 30. See, today only I can see it is only 34 students here. It is not only the class because you are actually missing so many good topics, so you cannot understand the next class again. Okay. Please send one message to all of you, all of them. Okay, this one.
Yes, sir.
Okay, thank you. And Akash, I'm not getting you, so I think you are muted and not talking. And what about Bora Arvind Reddy? Bora Arvind?
Yes, sir. Hello.
Yeah. So is it clear everything?
Yes, sir.
Okay. So you can explain, right, how sodium borohydride can improve the electrocatalytic activity, right?
Yes, sir.
Good.
Sir, I have mailed you. I was absent for one day, sir. You called my name Bora, but I couldn't answer because I was in station. I sent you a mail, but you didn't
Yes,
reply me.
yes. I got it. I noted it. No
Okay,
problem.
sir. I was there, sir. I was listening to the class, but suddenly I was in the station, so I was unable to. Network got disconnected, sir.
Yeah, I got your message.
Okay.
Okay, fine.
Thank you, sir.
Okay. Harshita?
Yes, sir.
Yeah, so everything clear how sodium borohydride can activate the surface, right? You can understand.
Yes, sir.
Okay, good. Okay, so let's now let's go back some detection technique. So we can use this method for the detection. Like you can see here, if you can see, like you can use this gold nanoparticle as a probe. Like here actually for the Instead of using the antibody, we are using the DNA actually. So we can activate this gold with some sodium borohydride, right? So if you can activate the gold sodium borohydride, you can get the better activity. That technique actually used. I mean, when you are like, if you think about the antibody, so you are labeling the antibody with gold, right? So you can activate this gold with sodium borohydride. Then you will get very high activity. That actually described in this figure. So this is the things, and here, see, it is the mechanism how. See, sodium borohydride. Any question, guys? I think someone. No. See, sodium borohydride means it is Na plus and BH4 minus. So BH4 minus, this anion has the, see, 4 hydrogen atoms. These hydrogen atoms, M means this is the nanoparticles, right? So this hydrogen can adsorb on this nanoparticle surface like this. And at the same time, hydrogen can remove from the solution. And this is called the catalytic hydrolysis of sodium borohydride. Someone wanted to speak something? Otherwise, please mute. Any question, guys? No? See, so here, if M, suppose M is the metal nanoparticle. So BH4 means sodium, this anion, BH4. So BH4 we can represent like this. So hydrogen can adsorb on this metal. See, metal, on this metal atom, hydrogen adsorb. And one hydrogen atom can bind with the water hydrogen, and hydrogen molecule can generate, and it can remove from the solution. And one thing, it can be done in the lower pH. Means pH should be acidic. Acidic pH. Then this hydrolysis will be fast for the gold. See, I am always mentioning this is for the gold case. But we can change the material. That I will come. First, see, this is for the lower pH case and gold case. It can be done very good way. And this catalytic hydrolysis, this is also called, because of this hydrolysis, the hydrogen can adsorb, and also hydrogen molecule can be, it can be, evacuate from the solution. So this is called the catalytic hydrolysis, and here actually self hydrolysis of the sodium borohydride. Self hydrolysis means when sodium borohydride means Na plus and BH4 minus, right? So BH4 minus itself can react with the water, and hydrogen molecule can be generated. And BH4 minus can adsorb on the surface, and hydrogen atom can bind on the nanoparticle surface, and one hydrogen molecule can be generated. First one, it is the catalytic hydrolysis, and second step, it is called the self hydrolysis. So self hydrolysis case only means BH4 minus can generate some hydrogen. Now see, so what's the problem for the gold, and why we wanted to change the material? So from the beginning, I'm saying this is for the gold, but we may need to change the material. But what's the reason? See, there is some reason. First reason, we need to incubate, or we need to this nanomaterial we have to keep in the sodium borohydride solution for around 15 minutes or longer, maybe 30 minutes. But for the biosensors case, it is long, quite long. So one problem, we need to activate that for the longer time. Another problem, lower pH. So why lower pH is a problem? Because at the acidic pH, or biological other material, they can be their activity can be hampered, they can be destroyed. I mean, they can be changed at a very acidic pH case. Not only that, when we are using the sensor surface, generally we prefer neutral pH or 7.4 pH. Okay, generally we prefer this pH. But acidic pH can be a problem, that's why. So for the gold case, that's the two problem when we are using the sodium borohydride. So first, longer incubation. Second is the lower pH. Okay. So how we can avoid this step? So that can be done. So see. So then why not use the then one step? I mean, see, why not use some other material so that we can avoid the longer incubation? We can use some maybe some nearby basic pH or nearby 7.4 or 8 pH, right? We can use. So for that, we can use some other material that is called the palladium. We can change the material. So we already found this, but it is still in the research. Maybe you can find some other material maybe, but it is already investigated that palladium case, this hydrogen adsorption is the very fast, and it can be done in the high pH. So these two problems can be solved if we use palladium material. So first problem, the slow problem, that we can make it faster. Second problem is the low pH, that we can done in the high pH or even in the neutral pH, that can be done if we use palladium. See the result here. When we use gold, in this case, see, we use 30 minutes, 15 minutes and 3 seconds incubation time. At the pH, suppose we use the high pH around 11. See, around 3 seconds and 15 minutes, there is not much change, right? You can see the two cyclic voltammogram here. But after 30 minutes in the blue, you can see the significant change of the CD. But in the palladium case, you can see 3 seconds and 15 minutes. See, they are almost similar. I mean, within a 3 seconds, the surface can be enhanced. Means very quick, just drop and done. But for gold case, it is taking, say, almost 30 minutes. So it is very fast enhancement. Clear? Guys? Hello?
Yes, sir.
So that's why we have to optimize the material. It is their own property. Means gold case, it can be done very long, longer incubation time we need. But palladium case, it can be done very fast. So here actually we use some detection procedure. You can see just DNA procedure, like capture DNA, then target DNA. Then we use the detection DNA. So you can think about the antibody also, like capture antibody, target, detection antibody, then palladium. Same thing, just we replace antibody with DNA. So if you use the palladium, in that case, so this activity will be very high. So I will show you some curve here. You can see if we use the palladium and sodium borohydride treatment technique, you can go almost 10 aptomolar detection limit. Aptomolar means the femtomolar, and then again aptomolar means very low. So see, this thing, like nanomolar means 10 to the power minus 9, right? Nano. Then pico means 10 to the power minus 12. Femto means 10 to the power minus 15, right? Like this one. And apto means again 10 to the power minus, I think minus 18. Let's check this one. I think 10 is 18. So quite low detection level you can go. So like this way. So if you change the material, palladium and sodium borohydride treatment. Okay, guys, is it fine? So it is rapid enhancement. Any question, guys? Hello?
No, sir.
Yeah. So this is just, you can use this technique for any kind of the biosensor. Some just general technique I told you today. So you can use this one for any kind of sensor technique you can try. Okay. Okay, let's take your attendance. I think so many things I taught you. This is enough for your Monday's class test. So if you have any question, anything, you can send me email also, because you have the class test, so I can clarify you. If you have anything, if you need any material, anything, any study material, I think I already uploaded so many things, right? Let's, I think it is enough, right, guys? If I see files, yeah, there is lots of material I just uploaded. It will be fine. I uploaded so many papers, some book chapters, some book. That also you can use. Slides are okay for your test, class test. But if you want to go for your higher study also, or for go for your research level, or if you want to think some of your own project, you can read those book also. Okay. Do you have any questions? Or otherwise, we can stop today's class.
Okay, sir. Thank you, sir.
Thank you. Thank you. You
Thank
can
you,
leave.
sir.
Thank you.
Thank
Thank
you,
you.
sir.
Thank you, sir.
You, sir.
Thank you, sir.
Thank you.
Thank you, sir.
sir.